Welcome to AI Paper Slop. For the last 5 years, basically every major AI breakthrough has been the result of doing, well, one thing, throwing obscene amounts of money and data at massive pre-training clusters.
Yeah, that's pretty much been the entire playbook.
Right. But a paper dropped on July 7, 2026 from ByteDance Seed. It's called EdgeBench, Unveiling Scaling Laws of Learning from Real-World Environments. And it completely flips that script.
It really does. It's massive.
Because we've essentially been handed the industry's very first post-deployment scaling law, the researchers mathematically proved that when AI agents are placed in real-world environments over, long time horizons, their improvement isn't just random trial and error.
No,
It actually follows this stunningly precise log-sigmoid scaling curve, like hitting an R-squared accuracy of 0.998.
And the sheer volume of data backing up that 0.998 number is what makes this such a watershed moment. We aren't looking at models solving toy problems in some closed grid world.
Or just passing static multiple choice tests, right?
Exactly. The researchers logged roughly 38,000 hours of continuous agent-environment interaction. And this was across 134 complex, multi-layered real-world tasks.
That's a ridiculous amount of compute.
Oh, it is. The models were actively writing code, hitting compilation errors, querying external judges, and then revising their strategies over and over.
So if you're an ML engineer listening to this and you're building or deploying agents right now, this level of predictability completely rewrites how you should view inference compute.
100%.
Because you can mathematically forecast how much smarter an agent will get just by giving it more time to interact with its environment. But, to even measure a scaling law for learning, you have to build an environment that forces a model to actually adapt rather than just regurgitate its pre-training data.
Which requires discarding almost every standard evaluation framework we currently use.
Yeah, because traditional benchmarks usually restrict agents to what, a few minutes?
A few minutes, maybe a couple hours if you're lucky. They're essentially just testing memory and zero-shot intuition. But EdgeBench was built from the ground up to test exploration, hypothesis generation, and the actual accumulation of experience.
And is broad, too.
Very broad. It covers 6 major capability families: scientific and ML, systems and software engineering, combinatorial optimization, professional knowledge work, formal math, and interactive games.
And the difficulty of these specific tasks is honestly hard to overstate. We are talking about asking an agent to implement an FFmpeg SU-scale engine from scratch in C++ Mac.
Or performing groundwater plume modeling using really sparse well data.
Right, or gravitational wave detection analysis. The researchers noted that these tasks take human experts an average of 57.2 hours to complete, and the extreme end takes up to 320 hours.
Yeah, these are not trivial tickets.
So to give the models a fighting chance, EdgeBench allocates a continuous budget of at least 12 hours per task.
And during those 12 hours, the agents are embedded in this really clever dual-loop feedback system.
Okay, break that down for us. What does that dual loop look like?
So first they have a fast, unlimited local loop. This means they get unrestricted access to compilers, linters, and local simulators, so they can test ideas in milliseconds.
Just churning through syntax and basic logic.
Exactly.
Yeah.
But then there is a slower, authoritative external judge. This judge provides hidden test scores or rubric evaluations. It's essentially simulating a client or maybe a senior engineer reviewing a pull request.
So the fast loop lets them iterate quickly, while the slow authoritative judge stops them from just overfitting to a flawed local test suite.
You nailed it.
But I gotta ask, 12 continuous hours of compute for a single task sounds incredibly expensive from an MLOps perspective.
Oh, definitely.
Traditional benchmarks are like giving an AI a closed book pop quiz, right?
Right.
EdgeBench is like locking it in a lab for a week with a compiler, a simulator, and a giant goal. But do we really need 12 hours? Why can't we just test them on a series of, say, 10-minute bite-sized tasks to extrapolate their capabilities?
Because a 10-minute task doesn't map to real engineering. Think about it. When a human developer or an agent drops into a massive, undocumented legacy code base or some novel scientific data set, those first few hours are purely orientation.
Oh, that's true. Just figuring out where everything is.
Right. You have to figure out how the local build tools work, decipher the state of the data, run sanity checks. Short horizons completely mask an agent's ability to hit a brick wall, decompose why it failed, and then use that failure as a stepping stone. You just have to give the model enough time to build a mental map.
Makes sense. So they threw 5 frontier models into this 12-hour gauntlet, right? They had Claude Opus 4.8, GPT 5.5, GPT 5.4, GLM 5.1, and DeepSeek V4 Pro.
And this is where it gets crazy.
Yeah, because regardless of the underlying architecture or the specific task, their performance trajectories all converge on the exact same mathematical formula.
The log-sigmoid function.
Right. S of t equals S max over 1 plus it's t mid divided by t, all to the power of beta.
Which sounds complicated, but if we break the variables down, S of t is simply the score the agent achieves at time. TS max represents the absolute performance ceiling for that specific model in that specific environment.
Okay, so S max is the absolute limit.
Yes. Then did mid is the exact time it takes the agent to reach half of that maximum score. And beta is the slope.
The speed of the learning.
Exactly.
Yeah.
It dictates how aggressively the model transitions from a state of low performance to high performance.
The predictability here is almost eerie to me. The R-squared fit is at or above 0.993, even when they extended the interaction horizons out to 28 hours.
And for a subset of tasks, they took it all the way to 72 hours.
Which is wild. It is so tightly bound to this curve that you can take just the first 6.5 hours of a model's run data, fit the curve, and perfectly forecast where that agent's score will be at the 12-hour mark.
With an error rate of less than a single performance point.
I mean, think about what that implies for managing agent fleets. You don't have to wait 12 hours to see if a compute job is going to fail. At hour 6, you check the trajectory, see the projected S-max is failing, and you just kill the job to save money.
The economic applications are massive. But honestly, the theoretical side is just as compelling. The researchers didn't just fit a curve to data points. They provided a deep mathematical derivation for why environment learning follows a log-sigmoid shape in the first place.
Right. I want to dig into that math a bit more because I get that the data fits a curve, but why this specific math? Why a log-sigmoid and not just a linear progression or a standard exponential curve?
They modeled the learning process as a frontier expansion on a latent task graph.
Okay, pause. I want to make sure we visualize this latent task graph properly. Are we talking about a literal dependency graph in the code or something more abstract?
It's abstract, but it maps perfectly to real-world problem solving. So instead of viewing a complex software ticket as one giant monolith, imagine the total task as a graph of nodes, where each node is a specific chunk of the solution.
Okay.
Some nodes are unlocked because the agent has already figured them out, and some are still locked. The rate at which the agent's overall score grows is dictated by the boundary between what it knows and what it doesn't.
Okay, let's say the unlocked fraction of the problem is x. That means the remaining unsolved portion is 1 minus x.
Yes, exactly. And the expected score growth rate is the product of those two fractions. So the mass of the unlocked reusable capability multiplied by the remaining locked opportunity, which gives you x times 1 minus x.
Oh, I see.
And in differential equations, a growth rate that scales proportionally to x times 1 minus x inherently generates logistic S-curve.
Because the progress essentially feeds on itself.
Right.
It's kind of like playing a strategy game like Civilization or Age of Empires. In the early game, you only have a club and one unit. You can barely explore the map, so your growth rate is slow. The value of x is tiny.
That's a great analogy.
And by the late game, the entire map is revealed, but there is no territory left to conquer. So 1 minus x is near 0, and your growth plateaus. But the mid-game is where your expansion just explodes, because you have maximum resources leveraging against a massive amount of open territory.
That is exactly the dynamic. The agent leverages the functions it has successfully compiled and the tests it has passed to unlock the subsequent layers of the problem faster and faster until it runs out of solvable bottlenecks. That explains the vertical S-shape of the curve.
But the formula doesn't just use standard time on the x-axis. It uses t mid divided by t to the power of beta, which means the effective time coordinate is actually logarithmic. It's log t.
Yes, that's crucial.
The S-curve only appears if you compress time logarithmically. So why does time have to behave that way?
To understand the time coordinate, we have to look at the fractal nature of these task graphs. Real-world engineering problems are highly self-similar across different scales.
What do you mean by that?
Well, when an agent searches for a solution, it exerts a linear amount of computational effort over raw time. But every time the agent steps up in difficulty, the sheer volume of the graph structure it has to navigate expands multiplicatively.
Okay, so it's essentially like digging a mine. The first few feet of dirt are easy, but the deeper you go, the wider you have to dig the pit to maintain structural integrity, right?
Exactly.
Getting just 1 foot deeper takes exponentially more time and effort.
Precisely. To achieve a linear 1-unit increase in the actual difficulty scale of the problem, the agent has to expend an exponential increase in search effort and raw time. So if you want to accurately map the agent's linear progress against the true difficulty of the environment, You have to take the logarithm of the raw time spent.
Ah, okay. And if the environment doesn't have that fractal structure, I assume the math breaks. Like if an agent is faced with a rigid binary bottleneck like a database password, it either randomly guesses or doesn't. There is no escalating structural search.
Right. It's just a flat line of zero progress until a sudden jump to 100%. The Log-Sigmoid law demands that the environment actually allows for incremental structural learning.
Which is why real-world tasks fit the curve so beautifully. I mean, software engineering and scientific modeling are fundamentally fractal.
They really are. Fixing a syntax error reveals a type mismatch, which reveals a logic flaw in a core algorithm, which then forces a redesign of the data pipeline. You are constantly peeling back layers of complexity.
Knowing that this mathematical structure exists is incredible, but seeing how the newer models interact with it is where the competitive landscape really comes into focus for me. The paper details this generational speedrun, analyzing models released between September 2025 and mid-2026.
And what they found was wild. Agent learning speed is doubling roughly every 3 months.
Every 3 months. But wait, how do we know they're actually getting better at learning and not just benefiting from contaminated pre-training data? Like maybe the newer model just happens to have seen the test set in its training run, so it scores higher instantly.
That's a huge criticism in evaluations, usually. But the methodology they used here to isolate pure learning speed is airtight. The researchers carved out an 18-task slice of EdgeBench where all the models achieved nearly identical starting scores on their very first attempt.
Oh, wow. So everyone starts at the exact same baseline.
Exactly. The models have zero prior knowledge advantage over one another. So any divergence in their trajectories over the next 12 hours is purely a result of how well they adapt to the environment.
And the newer models like GPT 5.5 and Claude Opus 4.8 just tear up that curve.
They absolutely do. And a critical factor driving that acceleration is statefulness. The researchers demonstrated that a continuous, stateful 12-hour run consistently outperforms independent restarts. You cannot simply run 12 one-hour attempts in parallel, discard the failures, and take the highest score.
Because you lose all the context. It's the difference between locking one developer in a room for 12 hours versus putting 12 developers in 12 different rooms for 1 hour, but none of them are allowed to communicate.
That is the perfect way to look at it. The single developer who retains the context of their own failed experiments, who knows exactly why a certain library doesn't work, is always going to produce the superior architecture.
Right.
And that reliance on historical context naturally leads to the ablation study they ran on Claude Opus 4.8. They wanted to see if the size of the context window physically altered the learning curve.
So they pitted the 1 million token context window against the 200K window on the exact same tasks.
Yes. And the 1 million token window provided a stable 4.4 to 5.8 point performance advantage.
But what's fascinating to me is that the gap didn't just open up at the end of the 12 hours when the prompt got full. It manifested early, and it structurally elevated the entire learning curve from beginning to end.
Right, because it seems the model uses the expanded context not just to remember more code, but to hold a much more complex multi-layered map of the task graph in its active memory. It actually changes the quality of the hypotheses the model can generate.
That makes total sense.
Yet when a model has limited context, it inevitably starts overwriting its own mental map. It forgets the specific configuration of a bug it encountered 3 hours ago, so it risks walking down the same dead end twice. The massive context window eliminates that regression.
But let me push back a little here. Wait, are the newer models like GPT 5.5 actually getting smarter at the meta skill of learning? Or are they just generating code at a higher tokens per second rate, basically brute forcing more submissions in the 12-hour window? Because if I can type 100 times faster than you, I might solve the problem first just by throwing spaghetti at the wall.
It's a fair question, but the data strongly refutes the brute force hypothesis.
Yeah.
The researchers tracked a metric called the effective submission rate.
Which is what, exactly?
It measures the percentage of an agent's total submissions that actively improve the best so far score. The newer models are not simply generating a higher volume of code. Their submissions are vastly more precise. A significantly higher percentage of their attempts actually move the needle. They are diagnosing the environmental feedback accurately, isolating the failure, and deploying really surgical edits.
To truly ground this, we need to look at the gravitational wave detection case study they highlighted, because it takes everything we just discussed, the fractal task graph, the stateful learning, the precision edits, and maps it to actual agent behavior over a 12-hour window.
Yeah, that case study is phenomenal. The task is based on the landmark 2016 paper that first observed gravitational waves from a binary black hole merger, GW150912.
Right.
The agent is handed the raw LIGO strain data and instructed to entirely recreate the published signal analysis from scratch. It has to output the correct waveforms for both the Hanford and Livingston detectors, generate the time-frequency spectrograms, and calculate the velocity and separation curves for the source black holes.
Which is not a simple script. They unleashed a codex agent on this environment. Over the 12 hours, it made 224 explicit submissions to the external judge. But only 27 of those submissions actually resulted in a score improvement of at least 0.1 percentage points.
But as we said, this wasn't a chaotic random walk. The model executed a highly structured diagnose, edit, evaluate loop that naturally fell into 4 distinct phases.
Right, let's walk through them. In phase 1, the agent just fights to make the problem measurable. It builds a rudimentary pipeline, replaces a highly noisy frequency estimate with a more stable baseline, and manages to hit a starting score of 42.8.
Then the agent transitions into phase 2, where it hits a severe bottleneck with waveform mismatch. A less capable model, or a model without stateful context, might panic here and rewrite the entire script, essentially destroying its own progress.
I've seen human developers do that.
Oh, we all have. But instead, this agent decomposes the failure. It realizes that reference anchoring and detector alignment are 2 separate subproblems. By isolating those components and searching within those smaller subgraphs, it nudges the score up to 52.3.
And phase 3 is where that exponential leverage of x times 1 minus x really kicks in. The external judge feedback makes it clear that the source dynamics, specifically the source mass calibration, are the primary roadblock holding back the rest of the analysis.
Exactly. So the agent completely stops tweaking the general signal processing code. For an entire hour, it focuses strictly on that one bottleneck. It makes 17 targeted submissions focus solely on the mass calibration, and the velocity and separation metric explodes from a 64 all the way to an 89.
That's a huge jump. By phase 4, the agent has built a massive amount of unlocked capability. It finds a stable core solution and actively protects it.
Right. It freezes the source model entirely and shifts to hunting down residual corrections.
Like the narrowband noise corrections and minute phase alignments specifically for the Hanford detector. This hypersurgical refinement phase pushes the Hanford waveform score to an incredible 95, bringing the final aggregate score across all metrics to 67.0.
It is literally acting like a senior developer.
It really is, like a staff-level engineer debugging a production outage. You don't rewrite the entire backend when a single microservice fails. You freeze the working modules, isolate the failing service, build a test for it, and surgically resolve the bottleneck. The agent is methodically traversing that latent task graph, unlocking nodes, and using the newly acquired leverage to pry open the next layer of complexity.
And because the behavior is so deeply methodical, the macroscopic result perfectly traces the log-sigmoid curve. The case study proves that the mathematical predictability of EdgeBench isn't a statistical artifact or, a trick of averaging random noise across hundreds of tasks.
Right.
It is the direct mathematical signature of structured, step-by-step problem solving.
The implications for the industry are just profound. Post-deployment learning is no longer a dark art or a collection of random prompting heuristics. It is a measurable, predictable, and rapidly accelerating scaling object, just like pre-training.
The scaling laws of pre-training gave us models that can speak and reason. But EdgeBench proves that if you provide those models with rich environments, rapid local feedback loops, and long horizons, their ability to convert that environment into structural knowledge scales just as reliably.
The foundation has definitely been laid. We now have the blueprint for engineering the next phase of agentic capability and the actual metrics to prove exactly how fast we are moving.
Exactly.
I want to leave you all with a paradigm-shifting question to mull over. If environment learning reliably scales with logarithmic interaction time, and we can accurately forecast a model's final capability based on its first few hours of exploration, how long until the economics of the entire AI industry pivot?
Well, that's a massive question.
Right. If you can mathematically guarantee that a specific model architecture will solve a complex engineering problem given 72 hours of rich environmental feedback, will we eventually stop pouring trillions of dollars into ever larger pre-training clusters? Will the future of AI just be massive, long-horizon post-deployment simulations where models simply learn on the job? Think about it. We will see you next time on AI Paper Slop.